taking a look at 1M from the back of chapter 6. This looks like a couple of different things are going on. So things I would highlight right away. What I see CO, so carbon monoxide. So I'm probably going to do some sort of migratory insertion, right, with a ligand, inserting some CO. I have everything numbered here, right? And numbered correctly. That maybe is not that obvious how it works, but that's the correct way to number this. You might not be able to do that right away. But what you can see here is what have we added, right? For sure, right? Just even looking at this, you know, there's no carbonyls here. The CO pieces must be coming from the carbon monoxide, right? The gas carbon monoxide, which you can assume is in excess. Right? You can assume that's in excess. What other piece are we missing? Where this OME where did that come from? That must have came from the solvent methanol. Okay. So just a basic analysis, look at that. Looks like we need to make a bond between 2 and 6, and then somehow cyclize this up with a carbon monoxide in the middle. Just overall looking at it like that. Okay. Next thing we want to look at is, okay, what kind of catalyst do we have? That is palladium. What's the oxidation state of palladium there?
0.
Palladium 0. Very good. So that's palladium 0. You can even draw the lone pairs in there if you want to. Now at this point, there's a couple of different things you're going to need to do. So maybe the first step is usually the hardest in some of these. All right, so one thing you maybe start to recognize, right, OAC could be a good leaving group. Because, right, what is OAC? So we remember what OAC is. Assay, which has resonance, well, of course, which stabilizes things. So that's actually a pretty good leaving group. So we're going to use the palladium like a nucleophile and kick out the acetate. Now, we could do this a couple ways. We could do it straight up SN2 style, just kick it out. Or we could do the SN2 prime style, where we attack 6, the pi bond moves over, and we kick it out that way. One thing you want to think about, what bond do you know we need to make? Looking from the starting material to the product, what bond do you know we need to make? 2 to 6. So one thing to think about is, well, we're doing organometallics. We probably want the metal on the carbon where the action's taking place. Right? So which carbon should we attack then? Let's attack 6. Right? So going there. Right, kick it out that way.
So if we're labeling that step,
that would be SN2 substitution, ligand exchange, or substitution really. Because now we got to be careful. There's going to be a charge. We got to balance our charge when we do this. So I'm going to redraw it. All right, so I've redrawn palladium. I've redrawn the complex. I had palladium attack carbon 6. The pi bond between 6 and 7 moved over and kicked out the O acetate. Now palladium has to have a plus charge because it lost 2 electrons. So you could also draw this, right? Also because it kicked out the O acetate, so there's a minus charge there. You could just draw it as the O acetate being a ligand of the palladium, and then it's just palladium 2 without a charge. Everybody see that? I could redraw this as these two things as bonded together. It's an ionic bond anyways. It's an X-type bond. So, I could draw it that way so then there's no formal plus charge on the palladium, and the O acetate's like a ligand at that point. So that's all that's going on. So now what do I need to do? What should we try to do? Let's coordinate to that. Let's coordinate here. We'll save ourselves the step. We'll say coordination. And then what do we else we need to do? We're going to do a migratory insertion. And we want 6, the electrons here, to go to 2. And one of these pi bonds now to be bonded, or the carbon 1 now to be bonded to palladium. Break that pi bond. Let's redraw that. All right, so I've redrawn this. I did 2 things here. I did a coordination, so I wrote that coordination step happened. And then I did a migratory insertion where carbon 6, the electrons between the carbon and the palladium went to carbon 2. The pi bond broke between 2 and 1, and those electrons went to palladium. So now palladium's bonded there. coordination and migratory insertion. I've also redrawn my ligand, or redrawn my catalyst as palladium-2 with the O acetate just on there. So instead of having palladium-2 with a plus and an OAC minus, just keep going along for the ride, I just put them together, and now it's easy to see that's palladium-2. Okay? So now, don't forget, let's go back to, remember, back up here, what we need to do, right? We talked about the first thing, just analyzing the starting materials and the products. We see that bond between 2 and 6, and then we see we need to add the carbon monoxide, the carbonyl group. So now we should start doing that. So what are we going to do? We're going to do a coordination and then a migratory insertion into the carbon monoxide the first time. All right, so I have it redrawn. Have the CO has been coordinated there. Now I'm going to do a migratory insertion from carbon 1 onto that. So those 2 electrons go there. The electron comes back there, indicating the formation of a new carbonyl. So redraw that now. All right, so we've done a migratory insertion. Carbon 1 attacked the carbon monoxide. One of those pi bonds came back down, reformed that bond, the sigma bond with the palladium. We net inserted that first CO bond there, first carbonyl. Now what do we need to do? If we look back up here, right, we need to seal this up. 7 needs to bond up to this carbonyl. So again, we could do a coordination, another migratory insertion. All right, so this palladium would be, of course, coordinated to that pi bond. And those electrons could go, they're going to go this way. And these 2 electrons are going to go to carbon 7. So the palladium's going to end up on carbon number 8 now. All right, so following that migratory insertion of the ligand here, so this carbonyl carbon and carbon 7 are now bonded. Palladium's now on carbon 8, still palladium-2. All right, so maybe I haven't been doing a good job of labeling my steps here. So I had a migratory insertion. I just did another migratory insertion. Guess what the next step's going to be? Another CO bond, another migratory insertion. Right, we keep using the metal, right, as a way to keep bringing these ligands together over and over again. All right, we're back again. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to do a migratory insertion. So this was a coordination here. The plate of the carbon monoxide. Then we're going to these 2 electrons go there from 8, come down. We're going to add that new, yet another carbonyl. So let's shrink this down. Let's shrink everything down. Everything needs to get smaller. All right, so following the migratory insertion of the CO, we're almost done now. We're almost done. This whole last piece, and the last thing we need to do is we need the O-methoxy, so we need to involve the solvent. So that's going to be involved is just going to do a ligand exchange at first, or SN2 type. Kick out the OAC. I'm just going to abbreviate this for space purposes. So that's a ligand exchange, like an SN2, you could call it. If I shorten this up, what we have left, palladium-2. Now with the methanol with the plus charge, OAC, just an acid-base reaction. Acid base. You have palladium-2. Now with the OMe on it, we just made acetic acid. The last step we're going to need to do is just reductive elimination. Two electrons go back to the palladium, single-headed arrows. Make the OMe bond. And that leads us to the final product, and that's just a reductive elimination. Back to palladium 0. So lots of migratory insertions, right? Lots of hard stuff to see kind of at first, but once you kind of start seeing it, it's kind of the same beats over and over. So yeah, one question would have been, could the methanol attack the carbon of the carbonyl? The only reason I would say it wouldn't is because, right, so let's think about nucleophilicity and acid-base kind of chemistry. This carbon of the carbonyl certainly is electrophilic, but is the palladium more electrophilic? Then how nucleophilic is the lone pair on methanol? It's probably more likely to use the metal to make this happen, right? Because then you'd have, you could do some proton transfers, but I think this is probably a more likely pathway, just based on how things react. Now, we did some ones where palladium was, right, if I drew it differently, maybe palladium as a positive charge. Again, I still think, you could do it other ways, but this seems the most reasonable for me at this point. Sorry, so if the question is, how do we know the methanol attacks the palladium and not the carbon of the carbonyl? What experiments could you run to figure out the correct mechanism? Of what? So you have this. How do I know? What experiments could I do to see if this is taking place or if the methanol is attacking the carbon of the carbonyl? So think about basic kind of stuff. Vary the concentrations of what? That's right.
The methanol. If it's going to attack the palladium,
Yep.
you know that's an SN2.
Yep.
Right, so it's second order.
Yep.
So,
Right. So yeah. So varying the concentrations of these things will help probe the mechanism, because if this is like an SN2 process, that means it needs both of these things. The other proposal as an addition elimination, that's a two-step process. That's going to be a little different, probably. And as we look at those concentrations, things could be a little different that way. So this is a one-step process, and the adding in, kicking out, that's a two-step process. So varying concentrations would probably be the most likely thing to do. Didn't say that well enough. So taking it back here, this first step, that's both an SN2 reaction and oxidative addition, right? Maybe I didn't say that clear enough. Those two lone pairs, right? Those two lone pairs, right, are being now used for a bond. This palladium is getting oxidized in that first step, right? So there was an oxidative addition in that first step, an SN2 and an oxidative addition. Good catch, yes. You can't do reductive elimination. You can't all of a sudden have a reductive elimination without having oxidative addition first, right? You must have oxidative addition first, and then reductive elimination at the very, very end. So the first step, more than likely, is this was an SN2, which was also an oxidative addition. Very similar to one of the homework problems we had. So another question is, since this first step is an oxidative addition and an SN2, is it possible to show this with radical arrows? Not in a clear way. This would be much clearer about what's going on and more representative of what the mechanism is. Trying to do this with the radical arrows just kind of doesn't fit. And sometimes that's the case. All right, 1J. Let's go ahead and take a look at 1J, just kind of analyze it from the start. Iodobenzene, and then this homoallylic alcohol. What's called homoallylic alcohol, when the pi bond is not in the allyl position, it's the homoallylic alcohol. And we end up with this aldehyde. So if you just look at this, we added how many carbons in the product? 1, 2, 3. How many carbons in this piece? 1, 2, 3. Right? So there's no CO coming in on anywhere or anything like that. So let's take a look at what metal we have. First of all, we have triethylamine is in there. And then our metal is palladium O-acetate, which of course is palladium 2. So I think we've done this enough where we know what the triethylamine is for. Triethyl, not diethyl, sorry. Where the triethylamine is going to be used to turn the palladium 2 into palladium 0. All right, so we should know how to do that. So I'm just going to assume we know how to do that and say, all right, palladium 2 to palladium 0 has happened. With the triethylamine, of course, the other byproduct was what? What do we end up with? We end up with probably acetic acid plus an N with the OAC minus, right? That should be our two byproducts. That gets us to palladium 0. So that happened. Good job. What's the next step going to be? What do we need to do? Oxidative addition into the iodobenzene. So now we got palladium 0. Oxidative addition. Palladium 2 now. With that. Nice. What's the next thing we're going to do? Let's coordinate. Let's coordinate. Let's coordinate there. What do we want to do now? Once we're coordinated, I'm going to number the carbons here. 1, 2, 3. Do a migratory insertion. How do I know I want to do carbon 1 and not carbon 2 to be bonded to the benzene ring? What?
That's the problem.
But what about, so
If you do it the other way, they'd be like a methyl group.
if you do it the other way, it'd be a branch product, not a linear product, right? So the product is linear, right? So we want to make sure the carbon 1 is bonded there so we continue to get a linear product, right? Otherwise, if we went 2, we'd get a branch product. All right, let's see what that looks like. All right, so we've done our, what step was that? That was a migratory insertion. So now we're here. How am I going to make an aldehyde? What can you do? Yes.
If you do a beta hydride, does it make an enol?
Yep. If you do a beta hydride elimination, you make an enol, which of course is just the tautomer of an aldehyde.
Is that right?
Absolutely. Right? So another way of thinking about this, right? In case you get stuck here and you don't see that, look at this product. The carbon here, right? To start with, the carbon that's bonded to the oxygen is bonded to how many hydrogens? To start is bonded to 2, right? Ever see that? The carbon that's bonded to oxygen is bonded to 2 hydrogens. In the product, how many hydrogens is it bonded to? 1. So you know you need to get rid of that hydrogen. How many ways do you know how to get rid of hydrogens? That beta elimination is a really good one, right? So even if you got stuck here and you're like, enol, what are you talking about? Hey, at the end of the day, I know carbon 3 needs to lose a hydrogen, right? It has 2, right? It has 2. And I need to take one of those off. And the only way I know how to do that is beta eliminations. At least one of the ways. So electrons go there.
But just goes off like that.
Beta elim. So palladium 2. 1, 2, 3. Do a reductive elimination with the palladium. That also generates what? HI, which of course, N palladium, 0 again. And the HI, of course, can be used to help facilitate turning the enol back into the aldehyde. Remember how to do tautomerization? Do I need to show you how to do that? Just a little refresh. Right? So the So I've shown you guys a quick and dirty way, but you could use the acid to do it. So what happened there? The pi bond attacked, so the H ends up on this carbon. The electrons between this O and H come down to form that pi bond. You generate I minus, but you also generate H plus again as well. So the product of this tautomerization, the taut, there's an H plus and the I minus, and this H is this H, ends up there. So this is an aldehyde, so H. So that's that tautomerization. Turn that into that. So yeah, the I minus, you can think of the I minus taking this H2, but HI is a strong acid, so it's fully dissociating this.